Good morning, everyone. So today we're going to do our lesson on the powers of rational numbers. So this is our last lesson for the unit. Essentially what we're doing today is just going over how to work with powers where the base is a fraction. So that's why we're talking about rational numbers. So we talked about yesterday we discussed how rational numbers kind of opens up um, our set of numbers. So we're looking specifically at decimal numbers, fractions, negative numbers, the whole gamut, right? So that's what we're going to be covering today. And specifically, I think the hard part will be negative fractions that are in powers. So let's get started. So I'm just going to review a little really quickly what you know about exponent laws so far. So just going through, I'm going to give you some examples and hopefully it'll kind of ring a bell. So when you multiply powers that have the same base, you simply add the exponents. And hopefully you remember that from grade 9. So for example, you would have 2 cubed times 2 squared. So we know that 2 cubed is 2 times 2 times 2. And 2 squared is 2 times 2. And of course, if I were trying to simplify this, I would simply be asking myself, all right, well, how can I simplify this further? Well, I know that there are a total of 5 2's being multiplied. So I can simply just add 3 and 2 together, and that ends up giving me 5. So that means that 2 to the power 5 is equal to this expression here. And we notice that 2 to the power 5, we get that from simply adding the exponents 3 and 2. So the rule here is when you multiply powers with the same base, you simply add the exponents. And when you divide powers with the same base, you can pretty much take a guess. We tend to do the opposite operation here, so we'll subtract. And the reason for that, just a quick little explanation here, and especially now that we talked about cross canceling, this might make more sense. We know that 2 to the power 6 is 2 times 2 times 2 times 2 times 2 times 2, and 2 squared is 2 times 2. So if we're dividing these two powers here, what we notice right away is that the 2's will actually cancel each other out. The two 2's, actually, there's 2 of them there that will cancel out. And then you end up with just 4 of them. And if you notice the numbers really carefully, you'll know that 6 minus 2 actually gives us 4. So this kind of makes sense with a couple of examples that we looked at, right? You can see here that if we divide powers, we simply subtract exponents. Again, we are going to talk about exponent laws a little bit more in detail, but just so you know, I'm just quickly reviewing this just so that this might help you better understand how we simplify powers that have a fractional base. So if I were to have a fractional base, and that means that, I have a fraction as a base, so that would be the large number, and I would have something like this, a over b to the power of n. The rule here is that you have to be careful with where the exponent goes. A common mistake, and I totally get why people do this, when they first look at this, they think, well, if I have some fraction a to the power of, a over b to the power of n, you would most likely think that you can simply do this. But that's not really the case. You can't just put the n, the exponent n, over top of the a. That exponent n actually has to be applied to the numerator and the denominator. And this is the tricky part. So the reason this works, let's actually look at this example step by step. So if I gave you an example, and again, this is what's a little bit difficult in math sometimes, is that we don't actually use numbers to represent this. We actually will sometimes use variables. And so again, these variables, if you look at this a over b, this simply represents any fraction, okay? This is any fraction, right? And we know that a fraction is made up of a numerator and a denominator. So we're simply saying let a be, for example, it could be 1, 2, 3. Let's make it easy. Let's say that a is 1 or 2 and b is 3. Right? So we have 2 over 3 to the power of n, right? If you want to, if you're getting a little confused by the variables, let's just actually use a number, right? But it's the same idea here. So what we're saying is we have some fraction raised to an exponent, and what does that actually mean? Like, what does that expand to? So if we have a over b to the power of n, what that means is I'm multiplying that fraction a over b a total of n times. So I'm multiplying it n times. Right? And again, n just represents a number we don't know. N could be, we could say you're multiplying it 5 times, right? So then if you're multiplying it by 5 times, that would be a over b times a over b times a over b times a over b times a over b. Hopefully I said that 5 times there. So how could we simplify this? Well, if I have a over b times a over b times a over b dot 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 all the way up to n times, we can simplify this by simply multiplying the numerators and then multiplying the denominators separately, just like we would multiply regular fractions, right? And when we do this, we actually are applying exponent laws, believe it or not. So if I have a times a times a times a times a, like if I just want to multiply the numerators together, I actually end up finding that multiplying all these a's together gives me a to the power of n. And it's a to the power of n because there's n of those a's, right? N of those numerators. And of course, it's the same thing with the denominator. We notice that there's b times b times b times b, and there's a total of n of those b's, so we write b to the power of n. And if you're having a hard time with this, I will do on this side, I'm going to show you an actual more concrete example if it helps. And I'm going to make it to the power of 4 just so I don't have to multiply that many times. So essentially what we're saying is I have 2 over 3 times 2 over 3 times 2 over 3 times 2 over 3. And what I'm essentially saying here is that if I multiply, if I want to simplify this, I can simply reduce this as 2 times 2 times 2 times 2 at the top, just like we have here, and 3 times 3 times 3 times 3, right? And then what I notice is that I can actually simplify 2 times 2 times 2 times 2. I don't have to write 2 times 2 times 2 times 2. I can actually write 2 to the power of 4. And then I also write 3 to the power of 4. And I'm hoping everyone starts to see a little bit of a pattern here. I noticed that I can actually just take that exponent 4 and simply apply it to the numerator and denominator, and I would get the same answer, right? So this is actually what happens in general for any fraction. And the reason I showed you how to do this, and you're probably wondering if it was so much easier doing it with an actual, with a real number, 2 over 3, why didn't I just do that at the beginning? Because I wanted to show you that this works in general, not just for 2 over 3, right? So in general, what we do is we simply apply the exponent to the numerator and the denominator. So the general rule here is we simply take a to the power of n, so the numerator to the power of n, and we divide by the denominator, which is b in this case, to the power of n. So one thing to be careful with, if the negative sign is not inside the bracket, then the power will actually be negative. And you're going to see some examples in the homework that are really difficult, in my opinion, because they're almost purposely trying to trick you with the negative signs. Just so you know, I'm not going to try to trick you with this. I will make it pretty plain and easy. But essentially what I'm saying is just like before, we talked about this last week, if the negative sign is not inside the bracket, you really need to be careful because the whole entire you have to remember that only the fraction without the sign is getting raised to that exponent. It doesn't actually include the negative sign. So it does change your question a little bit. So as an example, if I had a negative sign outside of this fraction a over b, and like I said, the fraction a over b can be any fraction there to the power of n, we need to remember that the exponent there gets applied to the numerator and the denominator, so to the top and the bottom there, but we don't actually include the negative sign until the very end. So we simply just put a negative sign in front once we're done the calculation there. And you're probably wondering what happens if it's inside the bracket. If it's inside the bracket, you need to be more careful than this. Okay, so that's what we're going to do next in the next part. Oh, went too far. There we go. So if we have a negative fractional base, then you really have to be careful with this. So if the negative sign is inside the bracket, then you need to watch out because the power could actually be positive or negative, and it really depends on the exponent. And if you're probably looking at if you're looking at this and you're like, this seems like deja vu, I kind of feel like I remember that rule from before. We did cover this rule, right? We actually talked about this already. We talked about how if the base is negative, then the power could be positive. Sorry, if the base is negative, the whole power itself could be positive or negative depending on the exponent, right? So if it was an even exponent, it would be positive. If it was an odd exponent, it would be negative. So we actually did discuss this before. The only difference with this is that we are actually looking at negative fractions. So we're making it a little bit more complicated, but the idea is the same. So essentially what we're saying in this case, if we have negative a over b to the power of n, it's the same idea as before. We're essentially just saying if it was a negative and the negative sign was inside the bracket, what that means is I'm taking negative a over b times negative a over b times negative a over b, and so on, a total of n times. I'm essentially multiplying negative a over b a n number of times, right? And n could represent any number, any exponent I could have, right? So 5, 6, or 7, whatever number I want, right? So what's important to remember is that if I put if the fraction is negative and I actually and if the fraction is negative and it's inside the bracket, then I really have to watch out for where it actually is going to be. I need to make sure that I include that negative sign when I'm doing multiplication, right? Now, you're probably also wondering about the fact that I have two different expressions that kind of look the same. So the reason I showed you two different expressions here is because this tends to be a bit of an error that people make. If a fraction is negative, they sometimes get a little confused as to where to place the negative sign. So the rule of thumb here is that you either place it in front of the fraction, right? So fully in front of the fraction, or we place it in the numerator. Those tend to be the most common options. You could technically place the negative sign in the denominator, but I talked about this already. It looks really awkward. So if I had put a over negative b, you can do that. It's technically correct. It just looks a little bit odd. And again, sometimes the textbook does do that, but I think they're doing that more to kind of throw you off or trick you a little bit. But in general, just so you know, when we talk about negative fractions, we either put the negative sign in front or we put it in the numerator. Okay, those tend to be the most common options there. So if I were to have negative a over b to the power of n, right, and the negative sign is inside, you essentially, just like before, look at the exponent, right? So if the exponent is even, then you know that your whole power is positive. And if it's positive, then really what we're saying is that negative sign has no effect on the answer. It's still going to be a to the power of n over b to the power of n. And we don't include the negative sign at all because we know that the sign of the whole power is positive. And if the exponent is odd, then we simply have to place a negative sign in front of the actual power that we find, right? So we would still do the same steps as before. Take a to the power of n and b to the power of n. And the only difference is the fact that there's a negative. It tends to throw people off, but really, you don't have to worry about, if a is going to be negative or b is going to be negative. All you have to remember is that your whole entire answer in the end, the power will be negative, right? And that's all we're really doing here. So these tricks really help you so you're not actually doing, so you're not overcomplicating your life, right? And thinking to yourself, okay, what's, negative, let's say as an example, I have negative 2. I feel like it's always easier if we look at real examples. Oops, negative 2 over 3 to the power 4. If I didn't have this little rule here, I would actually have to multiply negative 2 over 3 times negative 2 over 3 times negative 2 over 3 times negative 2 over 3, which, to be honest with you, it would just be a bit more complicated, right? You would have to multiply negative 2 times negative 2 times negative 2 times negative 2, which is positive 16, right? And again, be careful with the signs, right? So that's positive. Negative 2 times negative 2 is 4. Times negative 2 again is negative 8, and then negative 8 times negative 2 is 16. And then I have to multiply 3 times 3 times 3 times 3, which is 81. And then, while I did this, if I didn't use that rule, I would constantly be thinking to myself, is my answer going to be positive or negative? But if you use this easy little rule here, you know that the exponent is even, so you know that the answer will be positive, right? And then all you really have to do is take 2 to the power 4 and 3 to the power 2. You didn't really have to worry about that negative sign at all. So knowing this rule really does simplify a little bit of your work. You don't have to stress too much about the sign. Essentially, all you have to do is figure out from the beginning if the sign is positive or negative. But once you know that, then you're simply just raising the numerator and denominator to that exponent. That's all you're doing there. So I hope that kind of makes sense. Let's look at some examples with concrete numbers. I think it makes a bit more sense there. So evaluate each of these powers. So we have a couple different powers here, and you're going to notice the first one's pretty easy. The other two have fractions, right? So just throwing it off a little bit. So again, just a quick little reminder, because sometimes people kind of forget this. The rule that we just talked about, whether you're looking at the exponent, if it's even or odd, and figuring out the sign, that does not apply at all to A, right? I hope everyone's kind of clear on that, right? And why does it not apply? Because this base is positive. So any positive base, if I take any positive number and I multiply it by itself, X number of times, right? It doesn't matter how many times I multiply it, the answer will always be positive, right? So you don't have to worry when the base is positive. You only have to worry when the base is negative. And that's when we look at those rules. So in the first one, 3 to the power 4 to the power of 3. Sorry, 3 over 4 to the power of 3. Sorry, I don't know why I said 3 to the power of 4. 3 over 4 to the power of 3, so 3/4 to the power of 3. So using the rules that we just learned, obviously, just before we even start, I could multiply 3 over 4 times 3 over 4 times 3 over 4. This is still correct. I just want to let you know that this is still a legitimate option. And if you decide to do that, that's totally fine. But I do think that it starts to get a little bit more complicated. There's more steps in between. It's probably easier, to be honest with you, just to take each the numerator and the denominator and raise it to the power of 3. I think that's much easier. So 3 to the power of 3 divided by 4 to the power of 3, and that gives us 27 over 64. And that's it. And again, how did I get these numbers? 3 times 3 times 3 is 27, and 4 times 4 times 4 is 64. So you could have done it two different ways. I just wanted to show you the two different variations there. Next one, negative 5 over 7 to the power of 2. So in this case, be really careful because the base is actually negative and the exponent is even, right? So the first thing you want to do before you even start is actually just figure out what the sign of the whole answer will be. Well, going back to our rule, we know we have a negative base and an even exponent, so we know that the whole answer will be positive. So negative 5 over 7 to the power of 2 will definitely be positive, right? Before you even start, you know it's positive. So because it's positive, I really don't even have to worry about that negative sign. I just kind of put a reminder to myself that the answer is positive there. So I simply take 5 to the power of 2 and 7 to the power of 2 and figure out what my answer is. So 5 to the power of 2 divided by 7 to the power of 2, that gives me 25 to the power, 25 over 49 there. And that's it. The next example, we have negative 3 over 2 to the power of 3. So in this case, because the base is negative, but the exponent is odd, because 3 is obviously an odd number, we know that the whole power will be negative. So because you know it's negative, then we just kind of put a reminder to ourselves to put a negative sign in front of our answer, right? We know that the answer will be a negative answer there. And you could do it again. I just want to show you a different alternative. You could definitely multiply negative 3 over 2 times negative 3 over 2 times negative 3 over 2, right? And again, I always find it easier if you put the negative sign in the numerator if you are doing this method, right? And then we could do negative 3 times negative 3 times negative 3, which, doing a little bit of math there, is negative 27, and 2 times 2 times 2 is 8, right? So we end up getting negative 27 over 8. But to be honest with you, sometimes what happens when people evaluate it this way, every now and then people for some reason get a little confused, and they'll sometimes make the mistake of putting the negative in the numerator and the denominator, right? Don't make that mistake, right? Because remember, a negative divided by a negative is actually a positive, so that's not the same. So this is why I tend to tell students to avoid doing it this way, just because it does get a little bit tricky. It's almost easier just to figure out the sign first before you do anything else, okay? So now we end up getting negative 3. So we know that the answer is negative, so we just put a negative sign in front. And then we simply take the numerator and the denominator and raise it to the power of 3. So 3 to the power of 3 is 27, as we already mentioned, and 2 to the power of 3 is 8. So our final answer is negative 27 over 8. So let's look at examples where we're actually working with different operations here, with fractions. So this is where it just gets a little bit messy, right? Not necessarily hard. We've honestly have done examples like this. We already know how to work with BEDMAS. The only difference is that we never work with BEDMAS with negative fractions, right? It's just a little bit odd. So let's just look at some examples here. So let's say I have -2 3/4 minus -3 over 2 to the power of 3 plus -5 to the power of 2. This gets a little bit messy, right? As you can see here, there's lots of negative numbers, right? And this is what makes it a little bit confusing. So the first thing I would do is, just like before, we follow the order of operations. So we do exponents first, and then we subtract. But one thing to be mindful of, because there are negative numbers, you really, really want to watch out for the signs before anything else, okay? So first step, I know that I would try to figure out what the signs of the powers are. So I know that this power right here, -3/2 to the power of 3, will be negative. How do I know it's negative? Because the exponent is odd. And I know that this power right here, -4/5 to the power of 2, is going to be positive because, again, the exponent is even, right? So I already know right from the beginning, this will be this first power, -3/2 to the power of 3, will be negative, and the second power will be positive. That makes it a little bit easier, so I don't have to worry so much about the signs in the actual base. So what I do next is I simply I changed the first mixed number into an improper fraction. And the reason I do that, again, we talked about this. I personally find it a lot easier to work with mixed numbers versus, I find it easier to work with improper fractions compared to mixed numbers, right? Especially when you're doing order of operations like this. Of course, there are some times where mixed numbers are better. We have talked about that. But in general, when we're doing these types of expressions, I like to have one consistent type of fraction, right? So it's easier just to work with improper fractions the whole way through. So the first part, we have -11/4. I simply switch that into a mix, an improper fraction. And again, if there's a negative sign in front of the full fraction there. And then, of course, I am subtracting off a negative power. I already said in the previously that the first power would be negative. So because it's negative, I just put a negative sign in front, right? And then I simply take 3 to the power of 3 and 2 to the power of 3. So 3 gets raised to the power of 3, and 3 gets raised to the power of 3, and then 2 gets raised to the power of 3. And I simply put a negative sign in front. For -4/5 to the power of 2, I know that the whole power will be positive, so I just put a positive sign in front. And essentially, I'm not even worried about that negative sign anymore. I don't have to worry about it because I know that the whole power is positive, right? So that kind of makes my job a lot easier. I don't have to worry about, where does the negative sign go? Does it go in the numerator, denominator? Doesn't matter. The whole entire power is positive, right? So we simply take 4 to the power of 2 and 5 to the power of 2. So our next step, let's just try to simplify as much as we can. Go step by step here. So we know that 3 cubed is 27, 2 cubed is 8. So we're going to have -27/8 in the brackets. Keep in mind, those brackets are really important right now because we're subtracting a negative, right? So I make sure to not put the two signs next to each other to confuse you, right? That's why I put that bracket around there. So we tend to put brackets around the negative signs just to emphasize that, especially when you're subtracting a negative, just to emphasize that we're subtracting a negative, that we didn't make a mistake there. And then, of course, here we are simply adding 4 squared over 5 squared, which is 16/25. Then our next step, we notice here that we are simply taking a negative number minus another negative number plus a positive number. So really, before anything else, I would actually just try to figure out which operation we're doing in between the numbers, right? So obviously there's a negative sign in front. You don't have to worry about that. When we subtract the negative, we know we're going to be adding. And of course, the last one, there's nothing special there. You're just adding the fraction. So this actually makes it a lot easier. Instead of thinking about subtracting a negative number, which tends to really confuse everyone, we're just thinking of it as adding a positive number, right? Which is adding 27/8. So even though the power was negative, remember in this case, because we're subtracting a negative number, we're actually just adding, right? So now we end up getting negative 11 over 4 plus 27 over 8 plus 16 over 25. So this actually looks a lot easier than we initially thought, right? Because it did look like an extremely confusing question with lots of negatives, and in the end, there's actually not that many negatives, right? It just worked out that because we subtracted a negative power, we ended up adding, right? So now we simply have to add or subtract, well, actually we're just adding in this case, we're just adding the fractions. So first we need a common denominator. And by the way, I just want you to be really careful with this. Common mistake, like I said, is people just automatically think, all right, I'm just going to multiply all the denominators to find the common denominator there. But if you do this, you actually end up getting 800. And that's kind of a large number to work with in terms of a denominator. You want to try to see if there's a smaller number. And I'll be honest, the common denominator is still not that small. And I'll maybe skip the steps for how I found this, but it ended up being 200. And you can do the steps, you can just verify that yourself. 200 would be the lowest common multiple. And you can check 200 divided by 4, that works. That gives you 50. 200 divided by 8, that works because that gives you 25. And 200 divided by 25, that also works as well because we end up getting 8. So this actually works as our common denominator here. 200 is our common denominator, which means that we're simply going to change each of these fractions so that they have 200 as a denominator. And I actually didn't show the work there just because I was running out of space. And I also feel like I'm hoping you guys are okay with fractions. I think the hardest thing now is subtracting and adding fractions. I think the hardest thing now is just kind of combining all the rules. So I'm just going to briefly just show you how I found all the equivalent fractions before I show them to you. So for this one here, negative 11 over 4, how do I switch that to a fraction with a denominator 200? I have to think to myself, how do I go from 4 to 200? I multiply by, and in this case, I would multiply by 20, oh, sorry, not 25, I forget what it said, 50. So that means I have to multiply the numerator by 50 as well. And this is where students get a little bit confused because they don't know what to do with that negative sign, right? So we know that the whole fraction is negative, and I mentioned this already. If the whole fraction is negative, it's much easier, in my opinion, just to put the negative sign in front of the numerator. So even though I actually had it in front of the whole entire fraction there, I'm going to specifically put it in front of the numerator right here. So we're emphasizing that negative 11 is getting multiplied by 50. I wouldn't put in the denominator. It just makes it a bit more complicated, right? So negative 11 times 50, what does that give you? So 11 times 50 is 550, right? So we end up getting negative 550. So negative 550 over 200, that's our equivalent fraction. Now we're going to do the exact same thing for 27 over 8. So 27 over 8. I feel like I'm doing this with Christmas colors and getting in the festive season there, right? So I'm thinking to myself, how do I go from 8 to 200? So I'm going to be multiplying by 25. And then that means that I need to multiply the numerator by 25 as well. So we can just do the math here. So 27 times 25 ends up giving us 675. So 675 over 200 is our equivalent fraction. And then last but not least, and I think I'm going to do it here up top because I think I had more writing coming up, so I don't want to run out of space there. 16 over 25, we want to switch it to a common denominator of 200. So how do I go from 25 to 200? I multiply by 8. That means I multiply the numerator by 8. So 16 times 8 ends up giving us 128. So 128 over 200 is our equivalent fraction. So now we piece it all together. So that means that we have negative 550 over 200 plus 675 over 200 plus 128 over 200. And now that we have a common denominator, you can simply add the fractions up. So when we add the fractions up, we just, a little reminder, it's probably a lot easier to put the negative sign in front of the numerator, right? So we just simply put the negative sign in front of the numerator. That means we have negative 550 plus 675 plus 128. And all we need to do is grab a calculator or do this all in your head. Negative 550 plus 675 plus 128 ends up giving us, and I put the steps twice, I apologize, ends up giving us negative, 253 over 200. And of course, that reduces to 1 and 53 over 200 if we want to reduce that to a mixed number there. So hopefully that kind of makes sense. So again, it seemed like a really confusing question, but if you kind of go step by step with it, it should hopefully make sense here. And I apologize for the double step. There's no need for that. Sometimes I accidentally copy paste it too many times. So when I was copying the last step, I maybe went a little far. But essentially we are simply just adding up these fractions, which ends up giving us negative, 253. And then of course that reduces, if we want to write it as a mixed number, we can write it like that. And again, in terms of mixed numbers and proper fractions, I'm not too picky about which form you have to give me the answer in, but just there will be some cases where I will ask specifically for a mixed number or an improper fraction. So just kind of keep that in mind. Can you have a decimal base? Yes, you can. You definitely can have a decimal as a base. And if you have a decimal as a base, it doesn't honestly complicate it a lot. If anything, students find it a little bit easier. And it doesn't happen. We're not going to just, this isn't something we cover a lot in this course. And on the test, it won't be a big component, but this is still something that you should know how to do. So if you have a decimal as a base, then you simply just follow, sorry, I went too far there. You simply just follow the same steps as before. Just watch out for negative bases if you have a negative base. But other than that, you're still following the same rules as before. We always follow the order of operations. So let's do an actual more real life example. So let's say that you're investing $1,000 into a savings account. And let's say that this account gives you 5% interest per year. So that means you're actually going to earn 5% on your investment every single year. So how much money do you have after 5 years? So before we even do this question, just want to kind of be clear on what I mean by these the 5% interest. I'm not sure if any of you have learned about interest. You might have learned about this before. Interest is essentially money that the bank pays you for investing money into their account. It also goes the other way around. If you're borrowing money from someone, so let's say you're borrowing money from the bank, or you're borrowing money from your friend, I don't know, who knows, right? Then they would, if they charge you interest, what that means is they're charging a certain percent on what you borrowed, right? So what that means is if I invest $1,000 and the bank says I'm going to pay you 5%, then really I'm multiplying this by 0.05. And the reason I multiply by 0.05 is because that is the equivalent to 5%, right? So I'm simply taking 0.05 and I'm multiplying by 1,000, right? You're finding 5% of 1,000. And hopefully you have worked with percentage before. This is something, just so you know, we will review a little bit of percentage near the end, but this isn't something we cover a lot in the course. Unfortunately, which is really unfortunate. It's a great topic and this is great for you to learn, but we won't cover it as much. So I just want to briefly just talk about how we calculate interest. So we simply take 1,000 and multiply by 0.05, or you could take 1,000 divided by 100 and then multiply by 5. Either way, you should get $50. So how this works is after 1 year, you're gonna earn $50 extra, right? So even though you put only $1,000 in the account, at the end of the first year, you actually have a little bit more money. So after the first year, so I'll just kind of keep track of this here. After the first year, you actually end up getting $1,050 altogether in your account. That's pretty nice, actually, considering that you didn't really have to do anything. You just have to leave the money in the account, right? So then what's going to happen is you are now going to take 5% of this amount that you earned after 1 year. So take 5% of that amount that you just earned. So 1,050, I'm going to ask you to take 1,050 and multiply by 0.05. That actually ends up giving you $52.50. Now, if you put this in your calculator and you ended up getting 52.5 and you're wondering, why didn't I write 52.5? Because when we talk about money, we always want to include 2 decimal places, right? Because we're talking about cents. So even though I know we don't have that penny anymore, but we still use pennies with transactions there, right? So that means that after the first year, you actually end up with a total. So I'm going to put the total right here. You end up with a total of 1,050. Sorry, not 1,000. That's wrong. Let me just find the eraser here, because we are adding 1,050 plus $52.50. So we actually end up with 1,000. Sorry, $1,102.50. So we end up with a little bit more money at the end of the first year, which is, sorry, at the end of the second year now. So we're now on the second year, and this is what we ended up with, right? So after the second year, we ended up with this total. And then what we're going to do is we're simply going to figure out, we're going to kind of repeat the steps. We're going to take the previous amount, which was $1,102.50, and we're going to multiply by 0.05. We're going to multiply, and then we're going to add that on to the previous amount that I earned. So you can see here that this would be a little bit time consuming to calculate, right? This isn't like a fun calculation to do. It's just a lot of different steps. So there's actually different ways around it. So another easier way to do this, instead of actually figuring out what their interest is and then adding it on, and then finding out what 5% of that interest is and then adding it on and so on, it actually is easier if you multiply by actual rate of increase, right? So if you think about what's actually happening here, if I'm increasing this amount by 5%, I'm essentially saying I'm taking 5% plus I'm adding what I previously had. And the amount that I previously started with was 100%. So really what I'm doing is at every single step, I'm actually multiplying by 105%. So it's actually easier, instead of taking 5% and then adding it on, it's actually much easier to simply take the amount, which is 1,000 that initially invested, and then multiply by 105%. So in this case, it actually is a lot easier just to take 1,000 and multiply by 105%. And of course, 105%, just so you know, is going to be 1.05. Now, what I can do is I can simply take for the first year. So I'm going to do a little table here so we can keep track of this. I believe that my writing didn't actually go all the way through, if I'm not mistaken. So I'm just going to try to leave a little bit of space here. What I can do is I can actually keep track of what happens after each year. So obviously in the 0th year, at the beginning of time, there was only $1,000, right? After the first year, we take $1,000 and we multiply by 1.05. And we already found that amount. It was $1,050. After 2 years, so in the second year, we're going to take the $1,000 and we are going to multiply by 1.05 to the power of 2. And the reason we're going to multiply it to the power of 2 is because we're going to take 1.05, 1,000 times 1.05 times 1.05. So you multiply by the rate of increase 2 times, because it's happened for 2 years. And then you're going to calculate that amount. After the third year, you're going to take $1,000 and we're going to multiply by 1.05 to the power of 3, because we're multiplying by 1.05 times 1.05 times 1.05 for the total of 3 years. And I think you kind of see the pattern here. What do you think is going to happen in the fourth year? In the fourth year, we're going to take $1,000 and we're going to multiply by 1.05 to the power of 4, and so on, right? So we start to see here that the exponent there is simply representing the number of years that we're investing the money in. So there's actually a formula for this, and this is a formula that I will just give you the formula. You don't even have to worry about how we come up with it. You're actually going to learn a lot about this in grade 11. So, and I hope that you actually really take it in, because this is a really important type of math to learn for everyone, right? This is the type of math that everyone will need at some point in their life, right? So the formula to calculate the total amount that you have in an account is simply to take the amount that you invest multiplied by 1 plus the interest rate, and the interest rate is written as a decimal here, to the power of n, and n simply represents the number of years that you invest in, right? So what that would mean in this example, because we invested $1,000 from the beginning, I am simply going to take the $1,000 that I put in initially, and I am going to multiply it by 1.05. And again, it's 0.05, just so everyone knows, because we have to write it as a decimal. And I'm simply raising it to the power of 5 because there have been 5 years that have gone by. So we take 1,000 multiplied by 1.01 plus 0.05 to the power of 5. And of course, adding up 1 and 0.05, that gives me 1.05. And now my next step here, I need to make sure that I do the power first, and then I multiply by 1,000. So you can grab your calculator, and you definitely need a calculator for this. 1.05 to the power of 5. I end up getting 1.276281,562, and so on, right? But really, I could just keep a couple of digits there, and then I just multiply by 1,000. And my suggestion when you're doing these types of questions with large decimal numbers, don't delete the number from your calculator. Just simply keep it on there because you're going to need it for the next step. So I take 1.05 to the power of 5, and then I multiply by 1,000, and this ends up giving me $1,276.28. So I hope that kind of makes sense. Again, don't stress about this. If you're looking at this and you're like, I didn't really fully understand everything we did here. The main thing is, can you do the calculation here? That's honestly really what I want you to know. I bet like I said, I ended up explaining a lot more to you about compound interest than I probably should have, but I think this is just good for you to kind of be introduced to. But you're going to do more of this in grade 11 anyway. So don't stress about the actual, if you're kind of confused about, how we did the calculations here at the bottom or on the sides, don't stress about that. The main focus is that you know how to do the calculations use the order operations when there's a decimal base. That's really the main focus there. As long as you can grab a calculator and follow through these steps on your own, then you're good. All right, one last example here. And again, this is an example of compound interest, but just so you know, I will not put a question like this on the test. So the last example we're going to do, evaluating expressions by substituting. So if you are substituting, if you're evaluating an expression and you're substituting, what that means is you're simply replacing one of the variables x, y, or z, whatever variable you use, with the number that's given to you. So in this case, what we want to know is what is the value of this expression. So here's our whole expression here, when we are given that x is equal to -2 1/5. So all I really want to do is take -2 1/5, and I'm simply going to substitute it into x. That's all I'm going to be doing in this case. So what we do first is we simply replace every x that we see with -2 1/5. So we end up getting 2 multiplied by -2 1/5 to the power of 2. And again, all I'm doing is I'm simply taking my x that was previously here. There used to be an x there. Now I'm not going to write x anymore. I'm going to write -2 1/5. And now same with this expression here. I simply take the x that used to be in front of multiplied by 4, and I'm simply going to put in -2 1/5. Sorry. And again, just for a little reminder, whenever you see a number and a variable next to each other, it automatically means that we're multiplying them, right? So all I'm doing really is I'm replacing this expression that had x's with numbers now. So we have 2 times -2 over 1, times -2 1/5 to the power of 2, plus 4 times -2 1/5 minus 1. So my next step here, I know using order of operations, I have to square first. So I'm going to have to do the exponents. So I am going to take my fraction here, -2 1/5, and to make my life easier, I'm actually going to switch it into an improper fraction, right? So to switch it into an improper fraction, just be really careful with this. I know some of you had a bit of a hard time with this, switching mixed numbers into improper fractions when the mixed numbers are negative. So remember, reminder here, you can use the same rule that you used in elementary school, but you have to just be really careful. We take 2 times 5, ignore that negative for now, and then we simply add 1. So I'm going to show you the work here. So we end up getting 5 times 2 plus 1, and then we simply write it all over 5. And because it's negative, I just make sure that I put the negative sign all outside. So really, really important when you're doing this little shortcut from elementary school, ignore that negative sign, right? So we have 5 times 2, and then that gives us 10 plus 1, and so we end up getting 11 over 5, but then the whole fraction is negative, so I make sure I put a negative sign in front. So that's how I ended up getting a negative 11 over 5. So I have 2 times negative 11 over 5 squared plus 4 times negative 11 over 5 minus 1. And then in my next step here, I'm simply going to look at the sign. So I have a negative base, and obviously it's an even exponent, so I know my answer will be positive. So this is simply going to be 11 squared over 5 squared. And I don't have to worry about where the negative goes because I know the whole answer is positive anyways. And then I have 4 times negative 11 over 5. Nothing to worry about there. That's just a normal multiplication question there. And then, of course, I have minus 1. So my next step here is to simply figure out what 11 squared is. So 11 squared is 121, and 5 squared is 25. So I really have 2 times 121 over 25, plus 4 times negative 11 over 5 minus 1. And then going step by step here, what I'm going to do next is I'm going to multiply. So I have to multiply these two numbers, and I'm multiplying these two numbers right here. So 2 times 121 over 5. And again, just a little reminder, when you multiply a whole number or an integer by a fraction, simply put a 1 underneath it, and it automatically becomes a fraction. So I have 2 over 1 times 121 over 5. That ends up giving me 242 over 25. And 4 times negative 1 is negative 44, and 1 times 5 is 5. And again, I know that this answer in the end will be negative. And how do I know it's negative? Because the product here is going to be negative because I have a positive 4 times negative 11 over 5. So because my answer is negative, I make sure that I am subtracting there, right? So really what we're doing is just trying to figure out, is it positive or negative? And if it's positive, I add. If it's negative, I subtract. And in this case, it's negative. So I make sure that I subtract off 44 over 5. And then, of course, in the last expression, I have minus 1. Sorry, in the last part here, I have minus 1. So now we have 242 over 25 minus 44 over 5 minus 1. And we're near the end now. Now we need a common denominator in order for us to subtract. So the common denominator here would be 25. And again, if you're wondering what about that last number there, I can simply make it a fraction, right? 1 over 1. So now we end up getting a common denominator of 25, and then we switch all the fractions so that they have a common denominator of 25. So the first one doesn't change at all. 242 over 25 does not change because it already has a common denominator of 25. The 44 over 5, I'm just going to show the work here. To switch it to a common denominator of 25, I simply multiply 5 by 5, which gives me, I multiply 5 by 5 to give me 25. And that means I have to do the same to the numerator. So I take 24 and I multiply by 44, and I multiply by 25. And that ends up giving me, and I think I made a calculation error here. Yes, I believe I did. Oh, sorry, not by 25, it's by 5. My apologies, because 5 times 5 gives us 25. So 44 times 5 ends up giving me 220. And of course, the last step here, I have 1 over 1, and I'm switching it to a common denominator of 25, which means I multiply by 25. And I do the same to the numerator, and I multiply by 25, and that ends up giving me 25 over 25. And my last step here is I simply subtract these fractions. So I have a common denominator already, so I can simply add them. I can simply combine them together. So I have 242 minus 220 minus 25. And keep in mind that because I'm subtracting off that fraction, I can put that negative sign in front if that makes it easier. So I have 242 minus 220 minus 25. And what does that give me? So that gives me a total answer of negative 3. And I end up getting negative 3 over 25. And that's my final answer there. I hope that kind of makes sense. I know that was a kind of a lot, especially this last example here might have been a little tricky, but please look over it. I hope that the video did help. Definitely go through these steps and do the questions on your own once you've kind of looked at it, right? I would suggest redoing the question without looking at the solution and then just compare and see how you did. All right, and the assigned questions are right here. And again, a reminder, the asterisk means that it could come up on a test. Not a guarantee, but it could come up on a test. So hint, hint, nudge, nudge, you might want to go over it. And anything with an E just means it's an extra optional question, okay? Best of luck.